Hello students, today in this lecture we are going to discuss about the effect of solutes and impurities, how it how these affect the dislocation light. Now dislocation light is the primary mechanism of plasticity in metal. So we have a dislocation like half plane of atoms in a lattice. So this is so when we are applying stress, this dislocation moves. So this is known as the dislocation glide, and it is the reason for the plasticity, and it is especially found in metals and in ceramics as well at higher temperatures. So what is the effect of the solutes and the impurities if introduced into the material? What effect will it have on the dislocation light? That is the topic of this discussion. So firstly, you should understand that if there are solutes of the same valency, solutes having the same valency, then they are less effective in providing solid solution strengthening. Now, secondly, the nature of defects is important because the nature of defects, they may provide an extra charge, and that extra charge may cause a cation vacancy. Now this cation vacancy may lead to something called asymmetrical lattice distortion, and this lattice distortion will interact with the dislocation glide here, and it impedes its motion. And another feature is that we can mention here. So number 3, another feature is that there may be some charges which are univalent. The solutes may be of the same charges, univalent impurities. They produce a spherically symmetric distortion. So the previous distortion that we talked about while putting a cation vacancy, that was a tetragonal distortion, which is impeding with the dislocation motion. And it was caused by a cation vacancy. But if the impurities are of the univalent, that means not of any, no, there is no extra charge or extra vacancy being created, then that will lead to a symmetric distribution. And this symmetric distribution is mainly due to the differences in atomic size or elastic moduli. Due to differences in atomic size or elastic moduli. And these symmetric distortions will not interact as strongly as in the case of lattice distortion. So no strong interaction with dislocation glides, so they are not that much effective. So let us try to understand them diagrammatically. So if we have, say, combinations of cations and anions, say you have anions are usually of larger sizes, so I will put them in larger circles. So this is an company in a crystal. Now, if somehow we replace maybe this cation by a cation of larger size, and there is no, it is univalent, so there is no differences in charges. So this will lead to what we know as a spherical distortion, and it is not going to interact so strongly with the dislocation glide. However, if we have a cation vacancy, for example, this vacancy here, so this will cause a strain, and this will cause a lattice strain here, and also it is not univalent, so there is a cation vacancy created due to the impurity, and also there is a lattice tetragonal distortion. Tetragonal because the lattice strain is if this direction, that is why it's called tetragonal distortion taking place. So this will interact strongly with the dislocation glide. Now, addition of solutes and impurities to ceramics can also lead to strengthening. So what we are talking about, we are mainly talking about metals or ionic crystals, for example. Now, if we add solutes and impurities to ceramics, they will also lead to strengthening via precipitation of its striking phase. Will cause strengthening via precipitation of second phase. So if we plot, if we take an example how the impurities or doping effects in the case of ceramics, let's say we plot stress here in megapascals, and strain, and we take the example of magnesium oxide MgO being doped with ferrous oxide, ferrite Fe2O3. So if this is the this is the stress strain of a pure MgO, pure magnesium oxide. This will be the stress strain for 0.14% doping of Fe2O3, and to increase the doping percentage, this will be the stress strain. Say this is 0.55 percentage of doping of Fe2O3 into magnesium oxide. So you can see that due to precipitation hardening, you have higher UTS, tensile strength. The strength of the alloy increases, or the material increases.